Hello and welcome back to my Physics Online video lecture series. In today's video, we're going to be continuing our discussion of the Young's double-slit experiment. And the goal for today is to be able to locate the bright and dark fringes within our interference pattern. And in the previous video, this is part 2. Part 1, I talked a bit about phase effects, and so we had this nice spreadsheet that I've built in which we can look at what happens when you try to add two waves together based on differences in phase. And so if they're in phase, or this number that I'm changing right here, this is how many times pi phase shift between the two. And so if I change to an even number, you can see that the graph is unchanged. If I change to as long as it's a whole number, any 2, 4, 6, 8 is unchanged. And if I change to an odd number, they end up exactly out of phase. So that means that you've got peak and trough lined up together, and so when you add the two together, you get 0. The green line being the addition of the red and the blue. So blue line, thin blue line, thicker red line, thickest green line is the addition of the two. Any whole number gives us either perfect overlap or perfect anti-overlap. So here's 5 is no change. And if I have some non-integer number, let's say like 0.25, essentially what that does is it shifts the two curves relative to each other. So these two peaks are nearby, but they're not in the same place. When they add together, you still get a taller overall wave, but it's not as tall as when they're perfectly overlapped. See here, this is a value of 2. Each of these has a peak value of 1. If I go back up here again and make this 0, you'll notice that the green now has a value of 2 as the maximum. And in fact, this number below the number that I've been changing is the peak value of the maximum. And so if I have non-integer numbers, and you can make up whatever non-integer number you want, the two will not be overlapped, and so you're neither getting entirely constructive nor entirely destructive interference. In the case of the number that I just picked, we're closer to to an odd number, to 1, than to an even number, 0. And so it's more destructive than constructive. You can see that the green curve is shorter than the red and the blue curve. So we come back here, and the question is, why is it that these fringes appear where they appear? We've answered it partially here. Fringes appear where the phase shift between the two waves is equal to an integer number of pi, or dark fringes where you have an odd integer number of pi. So even numbered integers of pi, bright, odd numbered integers of pi, dark. And so what determines the phase shift? To answer that, we need to draw for ourselves this diagram again. So let's say that I have two sort of slits somewhere on the diagram. So slit 1, slit 2. And then somewhere way over here, I have my screen. Okay? And I've got light leaving from each of these two slits and arriving at the same point on the screen. So I've got light arriving here. I've got light leaving from the slit and arriving up here. Okay, and so this might be, we might label this as like point P where the two are arriving. And our delta phase, our difference in phase, we could call that delta phi. Delta phi is going to be given by 2 times pi times delta x over lambda, where lambda is the wavelength. So lambda represents wavelength of our light. Delta phi is the phase shift, or the phase difference, if you prefer, between light from the first slit, so slit 1, and light from the second slit, slit 2. And what we're going to do here is we're going to make an approximation. Okay? Imagine that this distance right here, we'll call it L, between the slit screen and the screen that you're projecting onto is very large compared to the distance D between the two slits. And D, of course, in turn is quite large compared to lambda. So L is many times greater than D. D obviously has to be greater than lambda. How many times greater than D should it be? Well, if you were to go to one of the biggest sort of science demonstration suppliers, Pasco, and buy from them a slit mask, they make them, then common slit separations might be like 0.125 millimeters or 0.25 millimeters, something like that. And so if you place this screen, let's say 10 centimeters away, then L would be almost a factor of 100, be a factor of 80 greater than the smaller of those, and a factor of 40 greater than the larger of those. And that's large enough for this to work. And frankly, most of the time when we do this demo, the slit screen is actually quite a bit farther away from the projection screen than just 10 centimeters. Like, I will often do it over a distance of 1 or 2 or 3 meters. So we're looking at, a few thousand times larger for L than for D. Now, one consequence of this is that although these two lines are intersecting at a point out here, if you were to try to measure what angle does each line make with respect to the slit, so let's say that I come in here and I want to measure what angle is this and what angle is this, I'd actually measure the same angle for both of these. So we're going to call that angle theta. And by convention, we just end up saying theta itself will be the angle between perpendicular to the slit mask and the point over here on the screen that we're interested in looking at. So this angle right here is also theta. These are approximately theta. The one in the middle is actually theta. How close to an approximation? Very close. You can go plug it into your calculator. You may have to go a few digits of precision before you see any difference. So they're effectively the same angle. Okay, the significance of that is that if I want to figure out the difference in path length, and to do that, what I'm going to do is kind of redraw. To get the difference in path length, what we do is we draw a line that is perpendicular to our two red lines, our two paths that are being taken by the light. And geometrically, this angle in here and this angle right here are equal. So that essentially means that I have, if I were to take this piece right here and blow it up, what I have is effectively a right triangle. So this is my right angle. This is the location of slit 1. This is the location of slit 2. So this side right here, that is the distance between the two slits, is the hypotenuse. It's the one that's across from the right angle. This angle right here is angle theta. And this side right here at the sort of base of the triangle, that would represent this side right here. This is the difference in path length taken from source 1 to point and from source 2 to point. So just using basic trigonometry, this means that d times the sine of angle theta is equal to delta x. Okay? And up here, we're basically looking for when is this an integer or non-integer value times 2 pi, or times pi, I mean. So I can take my first equation that I started with, and I can rearrange it so that instead of delta phi equals 2 pi delta x over lambda, I can say instead something like delta phi divided by 2 pi is equal to delta x over lambda. And what we need is for this to equal even numbered values of pi in order to get a bright, and odd numbered in order to get a dark. And so basically what that means is that delta phi over 2 pi, when that has an integer value like 1, 2, 3, etc., then that is going to give us a bright spot. And when it has a half integer value, like 1.5, or 1/2, or 2.5, or negative a half, negative 3.5, something like that, you get a dark fringe. Okay, so delta x over lambda is equivalent to saying if d times sine of theta over lambda is equal to n, then it's bright. And if it's equal to n plus 1/2, then it's dark, where n is an integer. So 0, plus or minus 1, plus or minus 2, plus or minus 3. Okay, so we've now located from these phase arguments, kind of like quasi-experimentally almost, like simulation experimentally, where the bright and dark fringes are. So bright fringe, I'm going to write this again big, because it's kind of the key point here. Bright fringe, if I multiply both sides by lambda, I end up with d times sine of theta is equal to n times lambda. And for dark fringes, d times sine of theta is equal to n plus 1/2 times lambda, where, again, n is 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. Any integer value. Okay, so we've located them. We now know where the bright and the dark fringes are. We can go a step further by coming back to the diagram again, and this time we just draw this perpendicular line all the way over to the screen and call this distance right here y. So maybe we want to know how far along the screen are our bright or dark fringes. Using a little bit of geometry, we can see that the tangent of theta must be y divided by L. I have a right triangle, this is L, this is y. And I've already solved for theta previously. In some sense, you can just solve these equations for theta. And so that gets you your y positions. One last thing, at small angles, this relates. And since sine and tangent and theta are all roughly equal, then we can find the position in terms of just theta using this equation, delta y L tan theta is L sine theta equals, basically solve these two for sine theta.